Good afternoon. Thank you for joining me for this video. I am Mr. Ish. We're looking here at a good, easy calculus, a relatively informal proof over here for a specific integral calculus property, a property of integral. We're going to prove it. Anyhow, this is what we have to show. You know very well if you have a given function and you want to find the area below that curve with regards to an integral, you have a lower limit a, upper limit b, and you can arbitrarily draw or define or divide that entire function into two parts such that you have an a to c and a c to b, and then you can create these integrals over here, these definite integrals from a to c f of x dx, which covers the area below this portion of the curve. Then from c to b, this portion of the curve is covered. You add them up and you can get that same representation as if you're doing the total from a to b. You know, this right here is a very fundamental property of integrals. In this video, we're going to show you why this is the case to be, why this property holds true. It's not going to be a long video by any means. So how do you go about doing this? And it's not hard, it's easy. Start by thinking about antiderivatives. There could be multiple ways for you to show this, but I'm going to show you a single way. If you look at this function f of x and you integrate it, you end up with something which looks like a antiderivative of this integrand over here. When you have this antiderivative at place, you know you have to end up doing a definite integration procedure because we have defined intervals here. Likewise, when you look at this function, it's all the same function, but it has been spanned over an interval and been split into two parts by this limit c. When you look at this function, its antiderivative is indeed that f of x, capitalized f of x, and you're looking at it in this form. When you have this, you're thinking about doing the definite integration procedure, upper limit, lower limit, and the difference of the two in both cases. Here you're going to get f of c minus f of a. Here we're plugging in the values into our antiderivatives. Here you have f of b minus f of c, and all of this should equal the definite integration output over here, which would be f of b minus f of a, which again here the antiderivative of f of x is a capitalized f of x, but then you're putting the upper and the lower limits, and you know very well you can get that. When you simplify all of this, you see something very amazing happen. The f of c's cancel out. You have a minus f of a plus f of b, which you can very well write as f of b minus f of a, which very well equals what you have over there, f of b minus f of a. So informally, you've proven this to be the case, that indeed you can take an interval a to b, you could split it up into any number of minor intervals so long as they are all connected. The property of integrals holds true, that they are all in a summation format. From the beginning to the end, all of these subdivided intervals of the main interval, they all have an additive property and they combine together to give you your whole interval. And the proof is right here in front of you. And that right there brings us to our closure of this video. I hope you enjoyed this video. Thank you for watching. Stay tuned. Have a nice day.